没有水波。
没有。
第二个最喜欢谁？
我说奶奶。
现在连黑的不多，应该。我比较相信这个让
可以还这个方面可以给到你们方面。
Solid state, come on. 295 state. Yeah. Did you speak Hindi? I do speak Hindi. Thank you for the email. Is that welcome? Yeah, welcoming here. Yeah. Okay, what do you say?
你好歹得加个王后边儿吧。
Swagatat, yeah, it's Swagatat. Welcome. Yeah, Swagatat means this is a welcome. That's what it says. Welcome is that's literally what it means.
找不着你，算了。
可以算出来一些非同小可以在里边带入，它说明这个创意资源是说有。
那种方法就是说，一个真正对一个真的能够像这些前面一个战略假定我的 manifold S1 space， 然后我让 S1 对S1 times S1 times this， 然后我想 preserve S1 从某个 structure， 我 reduce 我的 different modes， 我往往可以写作一个。你这个 S1 是什么 structure？ 就我S1 是 imaginary tensor group， 它应该是。我比如说我想 fix 我的路任何 radius 之间。然后问题是什么？然后问题是能不能就是说，因为我要 fix 我的 radius， 等于说我减少了我可用的那个different option。好像 keep S1 哪边的？S1 然后减少了我的 different option 了，然后应该有合规性，类似于 gravitational motion 3的类似于 gravitational motion 3的首先是 manifold 是 S1 和 quantum solution， 这两个之间可以插一个，比如左边和右边可以插一个manifold， 就它可以过去。然后来在上面写一个 x，
有一个明显的差。
主要是就是可以写一个管子上面是这样子。对，但还可以。我在想有没有其他的first order derivatives。
There's a table.
Sorry?
There's a table. Cuprate.
我想给书上写一个
Thank you.
一个 digression。你有什么条件？就是你要决定哪些symmetry，比如说这个是什么跟 invariant， 表现成那个什么跟 invariant。然后那个somewhat invariant， 就是你写什么，哪一个理由会想要它对于第一个 index 是这个 invariant， 第二个 index 不会。哦，你是说有 M 这样？
This is a phase and force. Yeah. this is
you
probably
reduce
two of
total
them.
set of can you reduce 你的 transformation 你应该可以更多 environment。
这样的，标准 vacuum controllers 有一个系数可以更要求。
Okay.
Today we are very happy to welcome Professor Subir Sachdev from Hubbard condensed matter theory. And as many of you know, he wrote a book about quantum phase transitions, and I admire his ambitions and the vision to import techniques from string theory to condensed matter and also the other way around. So today, in order to encourage people to ask questions, I also prepared posters. There are two of them. Professor Subir Sachdev. And then again, you are encouraged to ask questions as many as you can, and then we will ask him to sign. And then we'll give the person that Subir thinks the best question as good. And also, he's a revolutionary
What is
person,
this?
so there's a poster
Okay.
for the revolutionary. And so let's welcome Professor Sachdev.
Okay.
I don't want to
Never
say
had an introduction like that.
Let me try to say something in Hindi. Professor Sachdev ka svakat karahan. Did that make sense?
Professor Sachdev का स्वागत है. Oh, स्वागत करते हैं. Okay, yeah. We welcome. Okay, so I will tell you about actually work in progress with a number of people who are mostly in the audience. Dr. Joshi, Jen Gandhi, Ishwara, Risha, Tarapolsky, and Harvey Scamo. Actually, I realized just this morning there may be a snag in one of the things I'm going to talk about, so this is all still work in progress, just view it as that. So this is CMSA, but if you don't mind, I'll give some experimental motivation. So this is the famous phase diagram of the high temperature superconductors as a function of hole and electron doping. You have superconductivity on both sides, and in the middle you have an insulator, which is an antiferromagnet, which extends over different regimes, but much larger antiferromagnetism and electron doping than the hole doping. Anyway, the question that's largely driving our research is trying to understand what happens here at low temperatures in the regime where the DC is the highest. So this is where you get in YBCO, this DC will be much higher than this, it will be up to 90 Kelvin and so on. And what is going on there? And in fact, the puzzle really is that if you go beyond this, say, around 19-20% doping out here, then many of the properties, electronic properties that you measure by STM, by photo vision, and so on, completely fit the band theory. So if you give this crystal structure to a band theorist and ask them to work out what's going on, they will get almost everything right. On the other hand, below this dashed line here, if you try to compare the electronic properties of the normal state or even the superconducting state to band theory, they just fail completely. So the big question in the field has been, is there a phase transition here? Maybe there's a phase transition in a pure system, which is rounded out by disorder. Maybe there's no phase transition and just some very bizarre crossover, which is hidden by the superconducting dome. So you can get different answers to those questions even today, despite many decades of careful study of this field. I'll just show you some of the experiments. So for example, if you look at STM data, if you just look below this point, then you get this kind of picture for the dispersion of the electron near the Fermi level. All right, but that, in fact, doesn't look like band theory for the simple reason that you never get arcs in band theory. They just seem to disappear to nothing. On the other hand, if you go just a little bit above, you see that you do get complete curves. So this curve would, in fact, be just a circle. So you get a very simple circular Fermi surface of holes. You see that clearly. above this point. Also, if you look at the spatial structure of these modulations, then you see lots of density wave. This is just view of this as some kind of weak density modulation. You should see here a picture of the copper-oxygen square lattice. These are copper atoms here. And on the scale of a few lattice spacing, there's lots of density modulation on this side, but hardly any on the other side, and so on. So this is so that's one indication. More recently, there's another indication that something similar is going on. This is, for example, the specific heat. So the specific heat is linear in temperature in any metal. So if you go to, and now you, in this case, I think you measure the specific heat by applying a magnetic field to suppress the superconductivity. If you go to high doping, you get some gamma coefficient as it's called. But right near this 20% or so, they get a fairly well pronounced peak. So is this really a peak or at low enough temperatures, or is this just rounded out because of disorder? Well, these are the questions you can decide for yourself by looking at the data. If you look at the Hall coefficient again, at higher doping, you see exactly the value expected. If you take this Fermi surface, take the area, work out the Hall coefficient, that's the value. On the other hand, around 20% doping, there's a quite sharp drop in the Hall coefficient. Okay. Now, so one explanation for all of this could be, well, there's some broken symmetry. In the cuprate, it's clear, a whole doped cuprate, there's no magnetism. But maybe it's the charge density, this kind of charge density wave order responsible for what's going on. I would say my answer is that it depends what you mean by responsible for. It's there, and it may well vanish at some kind of phase transition in the pure system. But the underlying theory is something quite different. It's not just given by a theory of charge density wave fluctuations. Partly because these charge density waves are really tiny, especially when you get out here, whereas if you look here, this specific heat peak is quite well pronounced. And also the change in the Hall coefficient is quite dramatic. Okay. And of course, we saw in the talk by ZX Shen a couple of weeks ago, also something dramatic happening around the same doping, a different set of materials. He was measuring the superconducting state down at 0 temperature. And then when you looked at this velocity near the nodal point of the superconducting state, it was essentially doping independent all the way up to some doping, which is not something you get out of VCS theory because the TC is varying a lot. So roughly speaking, as TC goes up, the gap goes up. As the gap goes up, this slope should go up too, but it doesn't. On the other hand, on this side, it follows exactly like the TC is going down, the gap's going down, the slope's going down, everything is as you expect. All right, I think that's the summary of it. This is another plot from ZX where he, states the main puzzle with lots of different data that he presented in his book. All right, so that's the problem I want to talk about. I'm not going to answer it, but we're going to look at some simple models. And in fact, the basic model, I'll probably end up only talking about part 1. We'll see how it goes, depending on how many questions I get.
You have 19 minutes.
90 minutes? I just was lecturing for an hour and a half, so I might collapse in this 90 minutes. So I'm just going to talk about a toy model. So, and ask the same question. And in this model, we're going to make it very random. So, and if you make it very random, you automatically eliminate all kinds of autoparameters. Symmetry is not, at least translational symmetry is totally lost. And then you ask, in this model, is there a phase transition near at some doping? And what is it described by? So that's what I'll talk about. So here's the model. It's completely well defined, and we will hope that maybe in a few years we will know the answer at least to this problem. So this is very much like there's a long history in condensed matter physics for something. For the spin glass problem, there's the Shen-Kilpatrick model, This is in the same spirit. You have a bunch of spins, classical Ising spins interacting with random exchange constant. Just solving that, even in with fully connected interactions, turned out to be a long thing, but I think now it's pretty well solved, and it led to many new ideas and much insight into the problems. So the hope is that the same thing here. So what do? We take a bunch of n sites, okay? And on the n sites, you're going to put electrons that spin a half. So electrons can hop from any site to any other site with some matrix element Tij. And the Tij are just independent random numbers. Right? They're even complex. So these are independent random numbers. So now if you just had that term, that's just a random matrix, that's solvable. That gives you the Wigner-Dyson ensemble and a semicircular density of states. Okay. But we want to put interactions between the electrons, and we're going to put two types of interactions. A local repulsion, which will be constant on every site, and then an exchange interactions between nearest neighbor spins. And these factors of 1 over square root of n I have to put in to make sure the large n limit is well defined. Gives you all terms of contribute equally to the large n. Okay. So one question you may have is, why do I even need this term? Why can't I just take a Hubbard model with random hopping with j equal to 0? Because we know by super exchange mechanism, Hubbard model has exchange t squared over u. Well, so that particular model has been solved when you put j equals 0. That's DMFT. That gives you actually nothing interesting happening as a function of doping. It does give you a metal similar condition at half the length, which is also first order. But what happens is that if you compute the exchange coupling due to Tij, because of this factor of 1 over square root of n, the exchange will generate will be 1 over n, because it goes to t squared. And that has no effect in the large n limit. So you really need to put in some exchange by hand, which is much larger, about 1 over square root. So here's a model, and we try to solve it. Okay, and we don't know firmly the answer to any question really about this model. Well, there are a few things known, and I'm going to try to make a few more conjectures on what are the properties of this model. So, everyone know what we're looking at? Any questions?
Yes, it depends on maybe like do we put this on the square lattice with a periodic boundary condition?
Well, we'd love to put it on a square lattice, but then you're back to the completely unsolvable problem. But let's take this problem with just random Tij, completely coupled between any pair of sites, and let's see if we can solve that. So often when you have infinite range couplings, it simplifies things, right? Like in the spin glass problem, we simplified it. So we're trying to hope for something simpler. And if this has something interesting which looks like the cuprates, well, okay, then you can hope that you're understanding something generic. Yeah?
Does the distribution matter in this model?
No, actually. Basically, it will take zero mean to simplify life. And the important point is that they be independent random variables. Okay, so since there's random variables, to really solve it, you have to introduce replicas and honestly treat the replica method. I won't do it. I'll just assume that you can just do a replica diagonal average, because let's try to understand the phases where everything replica diagonal, which effectively means phases where things are self-averaging and you don't have any spin glass type model. So we're not going to look for spin glass phases, at least to begin with. Okay. So at least formally, it's possible to take this larger limit exactly. So you just write down the path integral for this Hamiltonian, assume replica diagonal, average over Tij and Jij. Then you get everything reduces to one-dimensional path integral. Okay. So sorry, come back to that. Okay. So reduced to one-dimensional path integral. So you just have a path integral of some fermion that lives in time. What could be more simple than a one-dimensional quantum problem? Or it's a one-dimensional classical problem, or a zero-dimensional quantum problem. So there's just one fermion, which depends on time, also has a spin index. And the action, first of all, this is just the single-site Hubbard model. Excuse me, the I shouldn't be here. Sorry, I should get rid of the I's there. Okay, so that's just a single-site Hubbard model. But these fermions have some long-range interactions. There's a long-range hopping in time, which we call R, and a long-range interaction in spin, which we call Q. And these R and Q have to be determined self-consistently. So R is itself the hopping matrix element, and Q is itself the spin formation. So this is the problem. So the problem now is find R and Q, so that this equation is satisfied. So Z depends on R and Q, and so you have to compute this coordinator in this interacting problem. So this problem's been around for 25, 30 years, and you could try to address it numerically. And it's only in the last few years, by a lot of the D and FT people like on George and Olivier Farquhar and others, that you're getting to the point where you're getting this numerically reliable results on this problem over different regimes. And some of the recent results are how I've inspired our work really on trying to get some analytical understanding of this problem. Okay, so you may not like, this is not solving the cuprates, but here's a problem I think will be solved in the near future. With the help of numerics and some of the tricks that we know.
No replica.
So I assume replica diagonal. Now, of course, if you want to do it correctly, these are matrices in replica space, and you have an additional replica index which you have to set to 0. Right. So,
It's replica diagonal and also the same for every replica, independent of.
yeah, so, right.
So we don't need a replica.
Well, I mean,
Right.
certainly there'll be phases like that where it's consistent. There could be other phases, you might instabilities where you do have to worry about it.
But that's the assumption.
For now, even the replica diagonal problem will be good to solve. Right. But as we'll see, in fact, what we have found is that there are certain regimes where you do have to worry about replica symmetry breaking. So here's the phase diagram I want to populate. On the vertical axis, you keep T over J to some number. The vertical axis 1 over U. This number proportion U. And this is the plane. So if I go to very large, very small U out here, then life is very simple. It's just a disordered Fermi liquid. Then you forget U. And the J's also don't matter very much because there's lots of charge fluctuation. The spins are not that important. And so the very large U, you're just going to get, this is going to be most important, very small U, sorry. And you just get the electrons hop around and barely interact, and that's just a disordered formula. And that does come out of the solutions in some regimes. Okay. But we'd like to know what's going on in all of this. All right. So first, let's look at a case where I take U essentially to infinity. So U is infinity, then what happens is that add the doping, and there's 1 electron per site, so the doping is 0. And you get 1 electron per site always. This will not be important because there's no hopping. The problem is just reduced to this. All right, so let's look at that. So that's a simpler problem. So now you have a path integral over spin a half. This is the spin vary phase. And there's only one function to determine, Q of tau, with this unequal in time interaction. And then there's a substitution condition, this Q has to be determined. So this problem is also somewhat difficult, given this simpler problem. Can't be solved exactly. But now there is numerical results on this problem. Okay. But if you now introduce another tuning parameter, so of course, so this problem here is just too hard to solve, and there is no, it's just strongly coupled. So you have to introduce, even for this simplified problem, other parameters. So what we did back in '93, in what is now become part of what's called the SYK model, is make another, introduce another parameter. So these are SU2 spins. So we wrote it as SUN spins, for example. So now you write your spin operator in terms of some pseudo fermions, and you let alpha go, so going to truly allow it to go to M. You've already taken the large M limit. Okay. Now after taking the large M limit, you take the large M limit, then this problem here reduces to these two equations. So the Green's function of the pseudo fermions, or these, is just given by this very simple expression, where this self-energy is given by, in fact, in this case, it's particle symmetric at low energies. Well, no, it's not. At high energy, it's not. So this is the exact answer. All right. So now if you reduce it to something that you can now analytically solve, at least at low frequencies and long times. And you can put it on a computer and solve it completely. This is, now takes a few minutes on a computer to get full solutions of the function sigma of tau as a function of temperature. And at zero temperature, the solution is the following. It's a highly non-Fermi liquid lactose solution. The Green's function goes as 1 over square root of tau, and the spin correlations go as 1 over tau. Imaginary. So this is some kind of spin liquid with spin correlations that are decaying at 1 over tau. And this 1 over tau decay, was interesting already to us in '93, because that is exactly the type of correlations you need if you scatter electrons out that you get a marginal Fermi liquid. So it's going to be connected to the marginal Fermi liquid phenomenology. And here this 1 over tau just comes out of the solution of this problem. You don't just know. This is also the solution of the SYK model now, what's called the SYK model there. The advantage is that you don't have to take the double limit, so it's easy to put on a computer, but you have a somewhat less physical Hamiltonian. Yeah.
This Sylvain is J squared G of tau or G squared of tau. Is it typo?
No, this is correct. J squared, J is just a number.
And the next one, G
Just a
squared.
number. So J is the root mean square value of the Jij. So
And then G squared of tau and G of minus tau.
that's all that is very crucial. Yeah, it's correct. There's no typo here. These are the famous SYK equations, or SY equations, actually. Okay, so you get this 1 over tau decay. So what can we compare this to? So for example, if you're in a Fermi liquid, if you're in a metal, then the electron Green's function would decay as 1 over tau. That comes from the constant density of states. If you have a disordered metal, the time decay of, because the constant density of states, the Fourier transform that just gives you 1 over tau. And the spin correlation decay is 1 over tau squared. So in a metal, in fact, local spin correlation in any metal decay is 1 over tau squared from the Fermi surface excitations. So this is a slower decay than the Fermi liquid. But it's not quite a spin glass. If this was a spin glass, this wouldn't decay at all and go to a constant as tau goes to infinity. If you found any phase where this is going to a constant, that's an alarm bell that you've got to put the derivatives back in to make sense of it. Okay. Just to, actually this solution, we understand, was understood fairly soon after our work, is to be an artifact of the large M limit, which is why people lost interest in this problem. But I'll tell you why. Hope is not lost soon. Why? So let's look at this problem in a slightly different way. Okay, so we go back to this problem. Can we analyze this without the large M expansion? Well, in general, you can't. But let's say we know that you're in some critical phase. So we only look for critical points. So, and see if there's any self-consistent critical point that could appear. It may not be actually there in the phase diagram, but let's see if it's at least a consistent saddle point. So let's just take this function q of tau and assume it has some power law. And we just look at the long time decay. So we just take q of tau and assume that it has this power law. Okay. And of course, then we take this q of tau and we forget the self-consistency condition. And then we have a well-defined problem. We just have a spin, which is in a time-dependent magnetic field. And this is some random magnetic field which has got this power law decay in this magnetic field. So that's what you could call as something like a Bose-Kondo problem. The way to think about another way to think about it is you take your spin. In this case, I've written the spin in terms of pseudo-fermions, but you don't have to. Couple it to some scalar field phi, and that scalar field lives in some auxiliary d dimensions. So here the picture is here's time, here's space, and actually, yeah, here is x equals 0, so it's sitting in the center of the space, and your spin is sitting here. So here's your whole line of time, and your spin is sitting here on this line. And you're just interested in the spin dynamics. So this spin couples to phi of 0. So we have some field phi above, in the bulk, and this phi will couple to phi of 0 and tau. S dot phi of 0 and tau is this thing. I haven't put the tau here because it's a Hamiltonian. And then what is the action for phi in the bulk? We just take a free massless scalar field. This is just a convenient way to write it. You don't have to write it this way. Just simple. So this can make the analogy to the Kondo problem. The Kondo problem, you have a spin at some position coupled to a Fermi liquid in the bulk. Here I have a spin at this position coupled to a free scalar field. Now, this is Gaussian, I can just integrate out the bulk field. And when you do that, you exactly find this problem. You get exactly this problem for the spin, where the q of tau has this decay. So that's how this is d-dimensional space, and d is unknown. You want to pick d so that the solution is self-consistent. Okay. D is you want to determine the value of d, and you can interpret d as a dimension of some auxiliary space, but you don't have to. It's just one way to write it. Okay. So now this problem has one coupling, this trilinear coupling, which is gamma. So it turns out that now you do some simple power counting. You find that gamma becomes important only below 3 dimensions. So let's just solve the problem then in 3 minus d expansion. So it turns out that in this expansion, this perturbation C and gamma can be done exactly. So you don't have to actually introduce any Lagrange multiplier or take any large n limit. You can exactly impose this constraint and just integrate over the fermions or at and order by order in gamma. So it's just time-ordered perturbation theory. You're just taking traces of various spin operators. The same way you do the Kondo problem also. And so you just do a beta function for gamma, assuming this power law decay. So one of the things you find then is that field phi has no boundary renormalization, and the flow of gamma comes entirely from the normalization of the spin operator here. And that allows you to make some exact results. So you do some perturbations here in gamma, you get some beta function, you find the fixed point, you kind of do two loops. And then at the fixed point, you ask the following question. You ask, what is, now you have to go back to this, so you found this, you have this theory where you took some power log decay of Q of tau. In some expansion, d minus 3 minus d expansion, you found a fixed point. Now what you should do, at that fixed point, compute this correlation function. Z at the fixed point, compute it here, and then see if it's self-consistent. Okay. But let's ignore the self-consistency for now. This is a well-defined problem. Given Q of tau, what is the right-hand side? Given Q of tau here, what is the right-hand side here? Yes?
So I saw that earlier you tried to eliminate the concept of the space. Is that right? So there's no space coordinates, but right now, later you also introduce space again.
Yeah, this is just, the RG turns out to be easier to formulate in conventional term by including space, but you don't have to. You can certainly formulate the RG completely in time.
Okay.
You can even make this ADS space if you want, ADS2, and it will work. It only depends in the end on the boundary correlation. Okay, that's, if you want to do finite temperatures, then the ADS can be Anyway, these RG equations, the point is, we're used to introducing these kind of pseudo-fermion operators. Then there's a U1 gauge invariance. And the Green's function of the F is a gauge-dependent quantity. So you get all kinds of, there's different ways of doing this where you put at intermediate stages have to worry about gauge-dependent quantities. But the final beta function is completely gauge invariant. It's just a property of gauge invariant coupling. And that's what it is, dependent. And there's about 2 or 3 different ways of deriving this, which are described in detail in these papers. Okay. So now what you want to do is determine the anomalous dimension of this operator, which is F tiger F. And here there's a very beautiful result that happens, that all orders in epsilon, as long as you're at a fixed point, this dimension is exactly this. There's no corrections at any order. And this goes back to the fact that there's no boundary normalization of this field phi, so the coupling constant normalization is very simply related to the wave function normalizations. When that happens, you get some exact exponent identities. So then this is the statement. So then writing in terms of t, here's the problem which we have solved, which we are very confident about. If you give me a single spin with a retarded in time interaction, which looks like this. So I assume Q of tau is this. And in that theory, where Q of tau is this, the 2-point correlation function of S of tau is 3 minus d. So it's really 2 minus that exponent. You have some decay of Q of tau is tau to the alpha. The decay of S dot S is 2 minus alpha. And that's what we show to all orders in this epsilon expansion.
So it's an inequality on alpha.
Sorry. This is for epsilon greater than 0.
Yeah.
Only then you have a fixed point. You have to be at the fixed point, at low enough.
Right. Yeah. So D has to be greater.
Well, D is between 1 and 3. It turns out it makes sense.
Okay. Only between 1 and 3. Okay. That's.
And of course, now it's just 2 lines of algebra that D minus 1 equals 3 minus D. The only solution is D equals 2, which gives you exactly the same decay that we found in the 1 over m expansion. So somehow that tells us that, so that's exactly this problem here, which was only a large n limit. So this tells us that there's no corrections to the exponent to all orders in 1 over m also. Or in epsilon. So there is some kind of exact solution waiting to find a place. But it's there. Okay. It's not an artifact of the large n limit.
So D
these three, this coupling is
Marginal, but you get all kinds of logs and so on.
and it's marginally relevant.
Yeah. This one, yeah, it's relevant. So this is the opposite sign, irrelevant, sorry. Gamma cube is irrelevant. All right. So down here, let's go back to our famous phase, this empty phase diagram. Maybe we have a point. We have claimed that there's some kind of novel spin liquid phase here with this spin correlation decay as 1 over tau. But pretty soon that hope was dashed. But people just took this Hamiltonian for SU2 and did some exact diagonalization studies. Just take 20 sites, but just diagonalize the thing, see what happens. Well, there was spin glass order. So at least for the SU2 model, there is a nice critical solution for SU2, but it's not the solution of this Hamiltonian, original Hamiltonian started. So the initial assumption that Q of tau is a power law decay is not valid. So what I showed here, that if this assumption is correct, then this is exact. That's what I showed. But the initial assumption may not be correct. At least in the ground state. So there's some, at best it's a metastable state.
Excuse me.
Yes.
Would you be able to define spin glass order for mathematicians like Professor Yao?
Well, it's simply the statement that if you pick any spin and compute it, it's this, so you have you compute this imaginary time correlation function. And the limit of the infinity is not equal to 0. That's the one that is the Anglo-Anderson type definition. I mean, it's also true for a ferromagnet, also, but here, since it's clear there's no ferromagnetic moment, this is good enough.
Why does it have to be imaginary?
Sure, you can do it in real time too, yes. But this is the time evolution of e to the minus h tau.
Do you have a space coordinates here?
So this is the same thing. You pick any side. So here, yeah, this is good. So here's the Hamiltonian. Here are just random numbers. Okay. Then you take the large n limit. Certainly you take the large n limit before you take the long time limit. Take the large n limit and solve this problem, where you compute on any site SI dot the local spin correlation. In fact, the answer, yeah, so this is not 0.
Do you choose the same site?
Sorry?
You choose the same
You
site?
have to choose the same site. If you choose different sites, it's just 0, it's much smaller. I mean, even if you take classical spins, or even if we just take these random number, then you have to go to finite temperature, of course. If these were just Ising spins, sigma I, sigma j, that's still a highly non-trivial problem. At finite temperature, that's the Shannon-Kirkpatrick model, which we know is true. So what this is showing you is that if you promote Ising spins to quantum spin-a-half variables, the Shannon-Kirkpatrick solution, well, the Parisi solution really, is still okay, qualitative. Okay. So, at this point, most people except a few diehards, not my students, but me and some of my friends lost interest in the problem in 2002 because of this. But recently I'm very excited to see this talk by Antoine George's group in the March meeting last year. Unfortunately, there's no paper yet. Where, all these are different axes, sorry, they have temperature and this is 1 over u. So the horizontal axis is the vertical axis here. Okay. And don't worry about temperature, let's look at load. So then this is the spin glass phase. So this point here was this point down here. Yeah, so actually they don't actually study. So what they're studying, sorry, I should say, what they're studying is numerically studying these equations, full original equations here. Just studying this, and it's quite a task. And finally, they have the state-of-the-art algorithms to do this without a sign problem. But they still, at the moment, at half filling, zero doping. And so here they find, this is the spin glass I just talked about. So Q of t going to 1 is just exactly the statement. Okay, same statement. And at very small u, like I said, Q of t equals 1 over tau squared. That's the disorder. Any Fermi liquid has a 1 over t squared decay of spin correlation functions.
Sorry, were those the replica diagonal equations?
Yeah, all, absolutely. So it's all replica diagonal.
Okay.
So certainly, if you want to understand this grayed out region, you have to include replicas.
Right. Okay. But
If
they
you
were
went
just
grayed out, they haven't studied it. We just know that something bad is happening there. But then they found what was very interesting. They looked at there's a quantum critical point. So this is an insulator, sorry, and this is a metal. It's an insulating spin glass and a disordered metal. Right at this point, they studied the spin correlations. Here's some of their data. And the same magic 1 over time appears. So it seems as if there is a place where this kind of SYK-like behavior, which we initially were looking for here, well, maybe it's going to reappear once you include charge fluctuations. Okay, this is pretty good numerical evidence for it. So that's the work now. It's great to start about modern work of the 21st century. Try to understand this and also what happens when you increase doping. So that's our recent work, inspired by this numerical result.
So is there a thought that you can just increase n and that just drives UC, that makes UC larger? So you kind of eliminate the spin
what are you referring to? M or N?
N, like the SUN kind of thing.
That's M. I'm calling that M.
Oh, sorry, yes.
N is the number of sites.
Oh, sorry.
Which is infinity to begin at the very beginning
Sure,
of the
sure.
game. Then M, of course, we want to be equal to 2, but yeah, well, using large M as a tool, but we certainly want to make M equal.
But here it's M equals 2.
Yeah, this is
This
for the
is-
physical case. N is infinity,
Yeah.
and everything else is no further approximation. It's the full solution of that random TJU model.
And
At half
SU2.
filling.
SU2.
Yes. Okay. All right. So this is then I can put a few more from that numerical result. I can put a few more points in this phase diagram. So what everyone seems to agree there's a spin glass here, and maybe for mysterious reasons this 1 over tau decay for spin correlation function at that point, and a disordered Fermi liquid. That's one. That seems to be what's appearing. So what we'd like to do is understand this, for example. So this is something that we've been working on, and it turns out that theory is quite a bit more complicated than another simpler theory that I'm going to talk about. Partly because the experiment's also not on this axis. The experiment's on this axis. And in fact, so far, this is not complete yet. We're finding this is not exactly 1 over tau. It's some other exponent to try to straighten out. May say something about that later. So right now, let's start with the spin glass insulator and increase doping. And the hope will be the same. What we're looking for is some critical point here. And just like over there, we're hoping that this kind of sort of rather robust behavior in these theories, that critical point may appear. That's one of our very new results, that we do believe there is a critical point here. And in fact, at that critical point, you have exactly this kind of criticality. Yeah.
So if you presume the criticality, do you then know it's 1 over tau by your earlier argument of that's the only way?
Well, you have to first, you have to identify a fixed point and look at the various operators of the fixed point. It's not a, it's not some kind of identity, it's a property of certain structure of our G flows. So, that's exactly the question we've been thinking about. It's not immediately true, and in fact, we are finding that for this critical point, there's some rather annoying operators that seem to destroy this effect. But for this one, you'll see. Okay. All right, so we take U very large down here, and then dope it. And so when U is very large, and then you basically don't want 2 electrons on any side. But you're happy to have either 0 or 1. At this point, every site has 1 electron, but once you change the density, of course, you have to have a few holes, otherwise the density won't change. So it immediately becomes a metal, but some kind of strange metal, not sure what. Okay, so we just going to take this problem with the double occupancy constraint. All right, so now, as I said, each site has 3 states. So there's the empty state, or 1 electron, up or down. So one way to do this is, but we don't have to do it here, in fact, is to write it in terms of some fermion operator F and a boson operator B, so that in terms of these operators, the electron operator is F B dagger and the spin operator is F dagger F, and then you have this constraint. So provided you impose this constraint exactly, you can rewrite the theory as a gauge theory of the F's and the B's. So this decomposition has a U1 invariance. So the way we're going to think about it is actually the generalization of what we just did for the pure J model. The pure J model, you had a spin operator, SU2 spin coupled to a bath. But now, we should really think of it as a super spin. The super spin is acting on 3 states, empty and W and simply occupied. So 1 state here and 2 states here. So there's 3 states. And the spin operator is like a rotation matrix in these 3 states. But so is the electron operator. This is also a rotation. But it's just like a fermionic rotation. So it's really a super spin, and there's a supergroup here. Something, what is it? I don't know what the precise word for it is, but it's like SU3, but one direction is fermionic. So is that OSP2/1 or something like that? I'm not sure. Anyway, so it looks like basically a supercondo problem. And the utility of that language is that you can do the gauge integral exactly. You don't have to impose the constraint exactly, and you can get results just in terms of gauge invariant operations. So you can write the path integral as a U1 gauge theory with an I lambda, which is imposing the constraint, and again now you have an electron operator and a spin operator determining R and Q self-consistent. So we're going to attack this in exactly the same way as before. You take Q of tau with some power of law decay and R of tau with some power law decay. In fact, I just realized this morning that this is not the most general assumption. There can be some particle Volage symmetry. So everything I'm going to say is modulo that Bulk discovered this morning, but I don't think it will have too much effect. It seems pretty innocuous, I'm pretty sure. Okay, so what happens here is you have this, it's really, the way to think about it, there's 3 states. There's the empty state, and the 1 spin, and the down spin. Okay, so this is our 3 states, and there's some spin operators that rotate between these states, some of which are bosonic, some of which are fermionic. And those are gauge invariant operators. And then this super spin is coupled to a bath. So basically, it's exactly this picture, except this is a super spin and this is a super field. This is a fermionic and a bosonic bath. So, and there's no real supersymmetry though. So that's why we allow the bosonic bath and the fermionic bath to have different exponents. There is some supersymmetric generalization of this for sure, but that's not very physical. To get supersymmetry, there's another generator here which is missing of the supergroup, which is the F dagger F minus B dagger B. and that's like the local charge density, and that has to also have a long lane interaction for you to get a supersymmetric curve. Anyway, so here's the fermionic path and the bosonic path, and then there's this local, the spin operator F dagger B or F dagger F coupled to the paths. But there's one thing else, and that's really crucial. There's this S0, which is like a magnetic field. So you have like a chemical potential term which changes the energy of these. You don't have to have the same energy. So it breaks the symmetry between the three states. And what we're going to find is that there is a critical point where these are almost degenerate. That critical point we're going to propose is what's separating the low doping and the high doping regions. Okay, so so it's a superconductor problem in a magnetic field. That's the problem you have to solve. Okay, so this is what Darshan and Chenwan have been working on, and these are their results to one loop. They almost have results to two loops. And basically here, it turns out everything that was true for the SY model is also true here. Everything that was true for the single SU2 spin is also true for this super spin. The only difference being that you have you have a field acting on the super spin. It's S. And this field is what's going to make this critical point. So it's a beta function for S, which is strongly relevant. Notice there's a 1 here. R bar and epsilon are small and proportional to each other. And these coupling gamma and G, which is the coupling between the super spin and the super bath, they flow to the fixed point. And again, all these things about exact to all orders can be applied in both cases. So you get exact exponents to all orders in expansion. And finally, you impose self-consistency, and you get, yes, exactly the 1 over tau decay of spin correlations, and also Fermi-liquid-like correlations for the electron. So, if you just look at this, you might say, oh, this is just a Fermi-liquid. But in a Fermi-liquid, this will decay as 1 over tau squared. The fact that these are not, even though this is Fermi-liquid-like, this is highly non-Fermi-liquid. It's really evidence for fractionalization. It's like a deconfined critical point, even though we can express it entirely in terms of gauging variant quantities. And in fact, you can do the whole thing with the other way. You can make the bosons the poles, the bosons the spins and the fermionic spin. It won't make any difference to this calculation. The whole thing is just gauging variant. And both the bosonic boson and the fermionic boson give you the same RG approaches. I mean, I guess the superspin is sometimes called the Hubbard X operators. And everything follows from the algebra of the Hubbard X operators, the whole set of RG equations. Okay, there's a lot of details that we haven't fully ironed out, and this is not written out, so like I said, don't post the video yet. But, okay.
So this is tuning the chemical potential, this splitting between the...
Yes, exactly. So that's the relevant coupling. So S, either flows to plus infinity or minus infinity. So if it flows to minus infinity, let's say loaded already. So S is, so if it flows to plus infinity, then you want to put all the charge in the boson, which means the boson will condense. And that means you have a disordered Fermi-liquid. The other side is not clear what happens, so it doesn't really tell you what happens on the underdose side. It's just flowing off to infinity and you don't know what's going on.
But you think that's the spin glass side?
Well, I'll come into that. So we can try to, we have to then go back to our other expansion method to see what happens away from the critical point. Right, so this is, so we certainly have found you have to tune some coupling where there's a fixed point with one relevant direction, which is this direction. It seems pretty clear on this side here that we have the same disordered Fermi-liquid. What's going on this side is not clear. Okay, so this is our main we have a candidate for a, there seems a very natural mechanism, even if it's very highly disordered TJU Hubbard model, for some kind of phase transition and some critical doping between two different states, one of which is and it's not, it's really like it's almost certainly on this side is, some kind of deconfined U1 case theory immediately described here, unless you get broken symmetry. And on this side is just, and the critical point itself is deconfined. It's in the sense of the fact that these two correlation functions are not, can only be understood in terms of some fractionalization. Okay. Now, of course, it would be great if this was tested numerically at finite doping for SU2, and this particular model put it on a computer. And I hope that there'll be a team at Flatiron working on that. And give us an answer whether you're right or wrong in the near, maybe in a year or two, I hope. So what happens here? Okay, so well, we don't know the short answer. So, but one way we can try to answer that is by taking the large M limit. So we want to take a large M limit in a way that we also get a critical point, and then we can compare the large M critical point with this epsilon expansion critical point, just as we did for the SY model. So it turns out you have to give both the fermions and bosons a color, and so M prime colors on the bosons and M colors on the fermions. So now your electron has both two types of colors, a spin and another orbital index. And then you get, it's very similar to like the SYK equations you get for the boson and fermion Rees function. These are of course not gauge dependent quantities. Now you've made a choice that the holons are bosons and the fermions, and the spinons are fermions. You have constraint on the chemical potential, and there are indeed, it turns out, there are solutions with all the right properties in the large M limit. There's kinds of fancy Luttinger-Wadded entities that we can learn about in this paper with Yang-Fei. But one thing that happens in all of the solutions is that delta F plus delta B is 1/2. And what that means is that it's exactly this. That means this is 1 over tau. So again, so you get consistency with, So in fact, if you take them both equal to 1/4, that describes a critical point. But here you in fact seem to get a critical phase, where this is true, where delta F is smaller than 1. No, delta B is smaller than 1/4, delta F is larger than 1/4. So that's some kind of pseudo gap type phase. So anyway, from the large M limit, it seems to suggest that there's in fact some other phase here with slightly different spin correlations. Spin glass eventually. But that seems kind of implausible to me. I think what the more likely scenario is this, that ultimately for SU2, it's just spin glass order, could be rather weak. It's a metallic spin glass. It's insulator only on that line. And then there's a critical point where you lose the spin glass order, and the key point, of course, is that this critical point is very much like a deconfined critical point. It's not something you can understand simply from a theory of the spin glass order. It's really a gauge theory of this fractionalization, which gives you the string exponent quoting the spin in the charge sectors. Okay, so that's that's our proposed phase diagram of the cuprates. Where the spin glass is replaced by other stuff. But you still have this kind of gauge theory describing a phase transition into conventional fluctuating. All right. Questions so far? Yes.
Is there a sharp definition of third gap in this model? Can we say the charge carrier is linear to x or log plus x?
Charge carrier is what? We haven't computed those things, but I think that's correct.
I mean, is there a definition, sharp definition?
Well, I mean, you try to compute conductivities and so on. You haven't done that. Yeah.
Can you define conductivity?
Yeah, sure, absolutely. Yeah. Well, you have to interpret this as a Bethe lattice or something, and then you can define it. I mean, it's very similar to DMFT like results. Yeah, well, that's a good question. Then this particular theory, when you so what you get in the large N limit is, this phase here is where the bosons are critical, they're not index. Here the bosons are index.
So it's a bosonic method, something like that.
Yeah, it's something like that. Yeah. But I'm not sure that's really correct. I mean, it may just be that ultimately it's just you do break the symmetry and it's a spin bus. So these are, I mean, this can only be settled, I think, numerically. People will have to really solve the problem, right, to see what's going on. But one of what we think, is the hope, of course. But even though there's all this complexity here, when you focus on the critical line, it's actually very simple. It's just a super spin, and there's a very robust reason for finding a critical point. Basically, these three states going through each other, and the super spin gives you a critical. Yeah.
But just to make sure, the figure you showed that was from this, I guess, the talk that.
Yes.
That was confined to exactly half filling is the
Correct,
point?
correct.
Okay.
So far.
And they cannot use their method, they get sign problems or something if they try to go away from half filling or is there a reason why they
I think this is the program, right? There's been a huge amount of progress in controlling the sign problem in these purely models in the last 3-4 years. There's a whole group at Flyband working on exactly that issue.
Right.
So they're pretty confident that they can do it now.
They think they will be able to do it.
Yeah. So there's all these diagrammatic Monte Carlo methods that have been developed, starting with proposal by Prokofiev and Svistunov.
Yeah.
And those have now been combined with DMFT, and there's a huge technology that seems to be ripe for use to extend these results to finite.
So, okay.
So we'll see. But so this kind of epsilon expansion gives us, and there's some results to all orders. I mean, so what I would say is, I'm pretty confident that if there is some kind of second order phase transition, it's described by the optics point. I mean, but I don't know if there is one. Well, at some level, you could say there has to be one. Yeah. Well, if there's spin glass order here, well, there's got to be some place where it disappears. So unless it disappears almost immediately, there is a finite doubling critical point. And is this the one for that case? But we'll see. That's our proposal.
So is there some notion of Luttinger volume in this disordered?
Yes. So that's what these relations are. So there's a particle hole notion of a particle hole asymmetry, these thetas. And they are related to the density of the bosons and fermions. So there's some more generalized Luttinger relation here between the particle hole asymmetry of the Green's function and the density.
But that's it for everything. It's not just the Fermi liquid regime or
The Fermi liquid regime has trivial exponents, so none of this really matters. There you just get a density of states, and that's it. It's a disordered system. There's no real notion of it. But when you're in the non-Fermi liquid regime, there is a notion of these particle asymmetries. It's not quite the same thing in Luttinger volume, but it is the analog of the Luttinger constraint. Normally there's a constraint that area enclosed by Fermi surface equals density. So here there's a constraint that this particle over asymmetry angle theta is related to the density. It's kind of a UV-IR relation because everything on the left-hand side is determined by the long time limit of the Green's function. Everything on the right-hand side is determined by the short time limit of the Green's function.
I mean, this Luttinger relation is some kind of anomaly.
It's an unknown, yes. Yeah. So if they can say a lot more about that in this paper, there's much discussion on this. Okay. All right. So I'm out of time already, right? You start. I've got to 1/3 of my talk.
You have still 30 minutes.
So let me just say a little bit more about the case that's been numerically studied so far. So this is of interest because of the numerics, not because of any particular experiment. And there, okay, you really have to go back to the full equations. And what we realized that there's a way to do that too.
Subir,
Yeah.
such is seminar ends at 12:15.
12:50.
Yeah, just get
Well, people should feel free to leave. You can still pick up the food. There's food outside. There'll be food, but you can leave and have food. Anyway, so you do the same thing, but now because you have charge fluctuation, it makes life quite a bit more complicated. It's not so easy to just make it into a superspin of 4 states, because here you really have to break the degeneracy at an early stage. If you don't break the degeneracy, you're going to just, well, effectively that means you're working at u equals 0, all 4 states at the same energy. And in fact, that's what we end up doing. We just do an expansion in powers of u. So that's the kind, you have to do an expansion in powers of u, and you get some rather complicated set of equations that Grisha has been working on. And here the whole thing is much more complicated. We haven't solved this out yet. There's still some inconsistencies in the RG equations and so on. Okay. Anyway, so that's, let me just stop with that. So this is what we know, at least from all our expansions, what's happening in the finite doping regime. And there seems to be quite robustly, at least at finite doping, existence of some critical point, even in the fully random sample, describing the regime where you go from where the holes are very mobile to where the holes are, where it's mostly the spins that are floating. Okay, so that's all I wanted. That was the toy model we've been studying, which it's amazing how hard that is, and hopefully we'll have an answer to that in the next few years. So the nice thing about that is that we can have a definite answer. We're not dealing with some theory that's impossible to solve. But if you want to do something more realistic, you have to do make a lot of assumptions based on the data and see their other, So let me describe some work that we've been doing. I think Matthias spoke about this also a couple of weeks ago. So I don't know if you want to really hear all the details. So here's another approach which doesn't put any randomness. But as we'll see, there are some features of what comes out of this approach that are quite similar to what we've seen in the random also. Okay, so here we'll start to begin with on the electron doped side. Why? Well, because there is a, an autoparameter at play, which is anti-ferromagnetic. So maybe that's really controlling everything here, optimal doping. And you can certainly write down theories of fluctuating antiferromagnetic autoparameter coupled to the Fermi surface, and does that describe everything? And there's recent evidence that in fact it doesn't. All right, so actually I cut out the evidence here. Maybe Matthias talked about it and showed all the data and so on. So here we start again with the same model, the Hubbard model, but on a square lattice. So this is so far very realistic. And we take the Hubbard interaction and decouple it by an auxiliary scalar field, which is a vector in spin space. And now everything depends on space and time. So if you just take V of phi to be phi squared and integrate out phi, you just get back the Hubbard model. But this phi, we're going to want it to condense at some point to get antiferromagnetic hole. Okay. But we don't want just boring old antiferromagnetism, we want something more exotic. And one way to do that is this trick of transforming to a rotating reference frame. So you imagine that the antiferromagnetic order is fluctuating from point to point. And so you define a local reference frame at each point, which is in the direction of the local order. So this is the physical antiferromagnetic order, and this is the order after doing the rotation. So what you want to do is you want to pick your R so that the H field is almost constant. And similarly, you rotate the electron operator by the same R to get some new fermions that are in the rotated reference frame. Okay, so this H field I'm now going to call a Higgs field. So if you're able to do this rotation consistently everywhere, where H is almost a constant, well, that would be like being the Higgs phase of this theory. Thank you. So why do I call it a Higgs field? Well, because this decomposition very naturally produces the gauge theory. Okay, so you've got an SU2 gauge transformation V that you can perform on these new degrees of freedom, the psi and the R and the H. And what you'll find under this transformation, that these relations, the physical operators on the left-hand side remain unchanged. Okay. So then now you have the original electron, the antiferromagnetic order, and now you have these new fields, the rotated fermion, the rotation matrix R, and the Higgs field H. And these are different physical and gauge charges. So in this case, so now we want to take some low energy limit. And the low energy limit is that we assume the Higgs field is dominated by fluctuation at pi. So now we're going to take a continuum limit for the Higgs field. Instead of taking on a lattice, we're going to assume it's near pi. And then you take this theory, and you find then three possible phases. There's the high doping phase, which is just the Fermi liquid, where you just condense you don't put R equals 1. You don't perform any rotation because the spin fluctuations are just totally disordered, so there's really no Higgs field around either. And on the other side, if you fix R equals 1 and you also condense the Higgs field, then that's just antiferromagnetic order. And this is, however, you get a novel phase in between, where the rotated reference frame is fluctuating a lot, but the Higgs field is constant. So in this case, you'll find that the Higgs field gives you small pockets, whereas there's no magnetic order because the frame of reference is fluctuating. And I won't show the data, but Matthias and Ziek-Shen have written a paper where they make a case that there's a regime in neodymium copper oxide between 0.14 and 0.175 where it seems to be in a phase like this. All right, so the critical point I described so far, the analog of that critical point here is this point here. So there's some kind of gauge theory because there's no broken symmetry on either side here, which is describing this phase transition from a metal with small pockets to a metal with large pockets, but no broken symmetry on either side. Phi is always just 0. Okay, so what is this theory? Well, here the actors are the Higgs field, but which carries a gauge charge. So the simplest assumption is that you just have a SU2 theory of the Higgs field. So this theory is exactly the SU2 gauge theory you'll find in your particle physics books. Except now the Higgs field is a vector, and it's coupled to an SU2 gauge field with some Higgs potential. Okay. So when the Higgs potential S is negative, then you're in the Higgs phase, the underdoped phase. When S is positive, you're in the overdoped phase. So now it's a well-defined question: does this theory have a phase transition? In mean field theory, it seems like it did, and it turns out the answer is no, it doesn't. And there's a kind of interesting story there. Well, what happens is the following. So in mean field theory, you would think you would condense the Higgs field. But it's a vector Higgs field, and that's the difference from the Weinberg-Salam model, where the Higgs field is not a vector of SU2, it's a spinor of SU2. So turns out that when you condense a vector of SU2, then it doesn't fully break the SU2 down. There's still a residual U1 symmetry corresponding to rotations about the direction of the orientation of the vector. And also, furthermore, there are monopoles in the SU2 gauge theory, which are basically the Atoff-Polakov monopoles. It's the original Atoff-Polakov monopoles, and this kind of theory is sometimes called the Georgia-Glashow model in particle physics. So there are these monopoles which proliferate associated with this unbroken U1. And so this means that there's ultimately confinement and there is no real Higgs condensation, even though it seems like it's developing. But it could be that this happens at very large scales, because the monopole action can become quite large, and so the monopoles will be very dilute. So there could still be a well-defined crossover, not a phase transition. So in this case, we find no phase transition, at least in this model. Okay, so this is replaced by a dashed line now. Experiments at some finite temperature, they couldn't distinguish in two phase transition. There's no thermodynamic evidence for a phase transition there in the electron open phase. Okay. So now if you try the same strategy for the whole doped side, you get actually much richer behavior. And the reason is just one simple change. All you do is you take the fact that the Higgs field at one wave vector that you observe in the experiments, the pi-pi spin correlations. Well, in the whole doped cuprates, if you do the neutron scattering, you don't see one peak, you see 4 peaks, corresponding to some kind of incommensurate spin correlations. So therefore, instead of having one vector Higgs field, you have 4 vector Higgs fields. And that's the magic. All you have to do is take this theory with 4 vector Higgs fields, and then you get, do the same type of analysis, which I will just skip. Here you find there's always a phase transition, which is possibly described by an SU2 gauge theory. And on this side, you have all kinds of broken symmetries or even topological order associated with these complicated Higgs fields configurations. So here the point I want to make is that this kind of phase diagram is very suggestive of what I showed you also for the totally random Hubbard model, where you had some kind of Fermi liquid on one side, a critical gauge theory describing a phase condition, some phase where for other reasons all kinds of broken symmetries appear. In that case, it was spin glass. Here, it's somewhat different. Well, these are very different models. Here, of course, the whole, there's one interesting, nice feature of this theory is, we took from experiments that you have these 4 points. And then just after that, we predicted, if you wish, that on this side, these order parameters can appear. And these are pretty much, apart from the last one, that are seen in various different experiments. And in every case, it would be wrong to write this theory as just a theory of these fluctuating order parameters. All right. But that was very fast, but okay, I think Matthias has talked about this. So finally, let me just say a little bit about putting the 2 parts 1 and 2 together. So they look like very different theories. This is also very much work in progress with Harvey and Matthias. So there's an interesting feature of the first part of my talk where I talked about these impurity models with all these Q of taus and R of taus that have been determined self-consistently. If you really look at all of those theories, they can all be written as partition functions like this. You want to go beyond the saddle point. So beyond the saddle point in certain large N limits, there are what we're calling bilocal field theory. Bilocals meaning that the fields really depend on 2 times, not on one that should be a tau 2. And then when you take the saddle point of such a theory, the saddle point depends upon time differences, but the fluctuations will then involve fields with 2 times. Okay, and in fact, this is the reason there's some connection to gravity and string theory, because you think of these 2 times. You have fields with It's described by 2 points in space-time, not 1 point. So that's like ends of a straight run, crudely speaking, but not really. So these are the kind of more complicated theories that appear in the first part of my talk. But here there's no space at all. And now what we realized recently is that if you take even this theory here and you couple it to the Fermi, so what I have ignored here completely are these fermions. There's also a Fermi surface floating around, which is coupling to the Higgs field. The simplest coupling is of this type, where the fermion density couples to the Higgs density. That's the only gauge invariant coupling allowed. And so, yeah, I'm going very fast here, but it's just to give you a flavor. So we start with this. This is just a canonical SE2 gauge theory with NH Higgs fields, which are vectors of SE2. And now what you want to do is you want to couple this field to a Fermi surface of electrons that are gauge neutral. And then you integrate out those fermions. So what you will get then is the gauge invariant combination of the Higgs fields at some time tau, interacting with the gauge invariant combination of Higgs fields. A and B are the gauge indices, with some object that decays in time. All right, so when you get something like this with the JF problem is 1 over tau squared, your first guess, if you're a field theorist, well, let me just figure out the power scaling dimension of this. So you just do mean field theory here, you get some scaling dimension of the Higgs fields, and you plug it in here, and you find it doesn't matter. So it's irrelevant by night power part. However, if you try to do a different approach, a large N approach, well, if you're doing a large N approach, you have to contract not the color indices, but the flavor indices, because if you have large N gauge theory, where N is the out of the gauge group, then it's hopeless. Large N gauge groups will give you string theory. So if you want to have any tractable approach, you have to take a large flavor expansion. If you try to do a large flavor expansion here, you find very naturally that you get a bilocal field. Because if you want to contract flavors, you have to contract a field here at one time with a field here at a different time. So you get a bilocal field theory, you look at its saddle points, and you find that the saddle point shows that this coupling to the fermion is actually not irrelevant. It changes some of the exponents. And this is still work in progress. Yeah, so let me put my conclusions. So random TJ model, it seems like it may well have a quantum critical point at non-zero doping with SYK-like correlations, separating a disordered Fermi liquid on the overload side to some kind of metallic spin glass on the overload side. And then I gave you this very quick overview of this SE2 gauge theory of fluctuating SDW order, which you probably heard a bit from Matthias. Thank you. Questions?
Can you say a little bit more about why you hope that the random model applies to a non-random field system? I understand that in the density DMFT, whatever it is. So you're getting you form an impurity problem. It's sort of assuming that you start with something with strong interactions and many nearest neighbors. It's sort of like a large nearest neighbor expansion.
So you can get very similar equations even for non-random models, but something in the large dimension limit. They turn out to be more complicated to work with. They've been working with those two, and then there's many other issues to worry about having to do with magnetic order, antiferromagnetic order, and so on. So taking the random model starting point simplifies the DMFT equations.
I understand that it simplifies it. I'm just trying to understand, why do you now hope that it's going to be correct for the? Is there some kind of intuitive feeling why it might be right?
Well, it's not
for the
sense
actual
of
problem.
exponents. It's definitely not right. It's not going to give you exactly the same behavior for sure in the finite dimensional system. So there's many arguments. Well, so if I go back to the beginning of my talk, there's all this evidence for some kind of singularity near optimal doping. So there's a question here. Is this a phase transition?
Right.
Even at that very
Yeah.
simple level. Suppose you have a random system which is a phase transition. Or if it is a phase transition, only because there's a broken symmetry. Okay. So the idea in partly here is, well, let's take a model where all these broken symmetries don't even have a chance. Do you still get a phase transition? So that's, and here, and there's always randomness in the real system.
Okay.
There's all, there's look at all the that's all due to randomness, everything you see there.
Okay,
It's not
yeah.
normal fluctuations, and so we want to understand something about the effects of randomness. Maybe it is important. It's a relevant perturbation in any clean critical point you might propose. And finally, of course, if you just take this critical point we found with a 1/tau correlation function, that immediately gives you all this margin of cumulative phenomenology and all of all these electron scattering experiments and various other transport experiments which fit the phenomenology of this model very beautifully. So all of the successes of these, rather, it's not understood why. There's also more recent work of people doing quantum Monte Carlo where it turns out that even if you take a non-random model, ultimately at very low temperatures it flows off to some universality class. But there seems to be quite a wide regime of temperature where you get exactly the type of behavior I've shown in the random. Yeah. So you get this local, space-independent criticality. You see that in many experiments.
So it could be that it's right
and
at small
simulations.
finite temperatures, but not really at very low temperatures.
Yeah, ultimately, if you want to understand a quantum critical point at finite doping in the presence of disorder, well, that's a difficult job. So this is for this kind of. So we're hoping to understand, include both strong correlations and disorder and finite density. Well, it's hard, and so we say, okay, well, let's at least take infinite range. Maybe we can solve that. And it seems to be very encouraging. That's all I can say. Please.
So I have a question about the last part.
Yes.
So you are introducing this Higgs order parameter.
Yeah.
It's essentially a SDW order parameter for the Fermi particle Fermi. So deep inside the base, I can imagine you can reconstruct the Fermi surface to a small hole pocket.
Yes.
That's good.
Yes.
But close to the critical point,
Yeah.
this order parameter should be very small. And the phenomenology may be very complicated. You may get a lot of small pockets. Is this a worry?
You mean that you get both electron and hole pockets? As
Yeah,
you go?
because the order parameter is small. You study a large Fermi
Yeah.
surface, we
Yeah,
find a
that's
small
okay.
order parameter, there are many pieces of
Yeah,
Fermi
so
surface.
that's a worry. So in fact, it depends how you formulate the theory.
But
Formulate the
in
theory.
your theory, it's a critical point of this order parameter, so it must be small, close to critical point.
If you assume that the hole-on Fermi surfaces survive all the way up to the critical point, you're correct.
Yeah.
But what could happen is that the Fermi surfaces actually are electron-like. They're bound states of this R and the psi. That's what we did in our recent. We assume they're bound states, and then you start from the large Fermi surface side. You have a large Fermi surface right at the critical point.
Yes.
Then you can ask, how does the fluctuation of the Higgs field give you spectral functions that look like small pockets? I think that's a calculation that Matthias may have described in his talk. No, this is a good question and bothers us a lot. In our current approach, we think, at least for the critical point, the best way to think about it is to come from the overdose side and just take a Fermi surface of gauge neutral fermions, which is large at the critical.
And in the critical point, in the two sides, I think you just introduce a non-zero Higgs order parameter.
That's the mean field theory, correct?
Yeah, that's the SDW order parameter.
Yeah, but what's happening in the fermionic spectrum is still a complicated issue.
Yeah, sure.
There could be rather strong short-range interaction between.
So are you trying to say that although in the mean field level we get along the pockets, but if we introduce gauge fluctuation, this may be killed?
I'm saying that you also, there may be non-critical strong attraction between the hole-on and the spin-on.
Yeah, sure,
at very short
of course.
distance. And that could make quite a difference, even at.
Yeah, that's beyond the mean field, we don't know.
It's certainly beyond me.
Yeah.
Yeah.
Sure, that's the.
But there are various strong coupling models where you can see how you get those pockets.
Yeah, that's the FR star.
Exactly, yeah. So we are working with FLs. In one paper, we worked with algebraic charge, but with another paper, we worked with FL star.
Okay.
And we,
I see.
okay, maybe you can understand the difference, but most people get confused, which is why I don't go into those details.
Okay. They are different, sure.
More questions? Before we thank Subir, they will be launched over there in the small seminar room. And let's thank Subir again.
I must have just gone and said your copy. I didn't realize it's all of a sudden.
Yeah, because
Yeah.
and your
Yeah, I went down to get a copy and then I got back up and checked my email. I was like, oh, that's something. So I assumed that I need that.
Yeah. Well, this is earlier than commercial.
Right.
Because mine is not much.
Yeah.
These are like a series of progress.
Yeah.
Several years.
Well, the main first part is very recent, only the last few months. It's very recent part.
You mean the very first part? The SYK?
Yeah.
The one with the UV and the heat
Yeah.
accretion. Yeah. But you say you have some interpretation from the anomaly, the integer theory.
Yeah.
Integer violation. Talk about like there's a additional new statement.
Well, I don't know how to. It's kind of an anomaly. From here, you can think of it as an anomaly as sort of Fermi that's what it is.
But in the previous statement,